Have you ever wondered how scientists decide if a new medicine actually works? Or if the difference between two groups of people is just a lucky coincidence? Welcome to the fascinating world of statistical significance. Today, we are demystifying one of the most fundamental tools in data science and research, the T-test. To understand the T-test, we first need to meet its creator. In the early 1900s, a chemist named William Sealy Gosset worked for the Guinness Brewery in Dublin. He needed a way to monitor the quality of stout with small samples. Because he wasn't allowed to publish under his own name, he used the pseudonym Student. This is why we often call it the student's T-test. It was a revolutionary way to extract big truths from tiny amounts of data. At its heart, a T-test is a signal-to-noise ratio. Imagine you are comparing the heights of basketball players and soccer players. The signal is the difference between the average heights of the two groups. The noise is the variation or spread within each group. If the signal is much stronger than the noise, the T-test tells us that the difference we see is likely real and not just due to random chance. There isn't just one T-test. There are three main types depending on your data. First, the one-sample T-test, used when comparing a group against a known standard, like checking if a cereal box actually contains 500 grams. Second, the independent samples T-test, used to compare two separate groups, like men versus women. And third, the paired samples T-test, used when you measure the same group twice, such as before and after a training program. Before we run the math, we must respect the assumptions. For a T-test to be valid, the data should follow a normal distribution, that classic bell curve shape. The variance, or spread, should be similar between groups, a concept known as homoscedasticity. Finally, the observations must be independent. One person's data shouldn't influence another's. If these hold true, we are ready to calculate the T-statistic. The T-statistic is calculated by taking the difference in means and dividing it by the standard error. But the number itself doesn't tell us much until we look at the p-value. In statistics, the p-value is the probability that the difference we observed happened by pure luck. Usually, if the p-value is less than 0.05 or 5%, we reject the null hypothesis and conclude that our results are statistically significant. Let's look at a real-world example. Imagine a company claims their new turbo coffee increases focus. We take 30 people, 15 drink the turbo coffee and 15 drink regular coffee. We measure their reaction times. By applying an independent T-test, we compare the mean reaction times. If our T-value is high and our P-value is low, we can scientifically back the claim that the coffee actually makes a difference, rather than just being a caffeine-fueled placebo effect. In summary, the T-test is the bridge between raw data and scientific certainty. It helps us navigate the uncertainty of small samples and provides a mathematical framework for discovery. Whether you are brewing beer like Gosset or analyzing clinical trials, the T-test remains an essential pillar of modern science. References: 1. Gujarati Dinan, Basic Econometrics. 2. John E. Friend, Elementary Business Statistics. 3. Student, William Sealy Gosset, The Probable Error of a Mean, 1908.